waiting for all the reactions, I'm going to send you guys a minute ago. I just had some things that came up, but I'm not going to be able to do it before class today. All right, let's cover this first reaction that you guys have on your list. All right, so we're gonna actually do this in real time. We're gonna use the same reactant, but we're gonna change the reagents, and we're gonna see how this will give us different products. All right, first you had this CH2N2 reagent with light. All right. Can anyone tell me really quickly what did they found out about this? What type of reagent is this? There's some students that need to get into teams. That's fine. All right. Because it's of time constraints. This is a cyclopropionation reaction. Right. So what does that mean to have a cyclopropionation? Anyone? All right. I'm gonna create a cyclopropane ring. Right. So my alkene here, my double bond, is gonna get converted into a three-member ring. Right? To make a three-member ring, these two atoms, well, let's not do that. That's gonna be confusing. All right, these two atoms here need to be on the same side. So I just get a ring here, okay? So if you think about the questions, what happens, or what atoms are adding in, right? That carbon here, let's make this in red really quickly. This carbon is being added. It's not gonna let me do that here. All right, so there's one atom that's being added to this ring, but both carbons of the double bond are getting addition to that carbon, right? So regional selectivity is not a concern because both carbons of the double bond get the same atom. So we know what happens where is not a question here because both atoms are getting the same thing. And then we need to know how, all right? This is a syn addition, right? So you want to think about that. This carbon that's being added here, the central carbon, are added to the same side, right? That's the only way to make a ring. I can't make a bond up top and one in the bottom. So they both are going to be wedged. But a lot of times we don't even consider that or the cis and trans or the anti or syn addition. But technically this is a syn addition. All right. Again, I will send a video out explaining all these reactions and details and the answer key to your activity sheet. All right. So you want to make sure you look at that before you attempt your exam. Okay. And you're more than welcome to use any other resources as well to be comfortable with things. Right. Let's move on to the next reagent here. All right. HCO3 and water. What's going on here? All right. Did anybody find anything out about this reagent? All right. This is an hydration reaction. Right? And if you want to be more detailed, okay, this is known as just an acid catalyzed addition water. All right, so some people might just even call this just an acid addition of water. What's important about this reaction? I'm going to put the detail below it. All right. This happens with arrangements. That means that the intermediate here is going to have a carbon cation. Right? And again, if you want to look into that detail, take a look at the video. Right? So what you need to imagine, and I made just a big mistake here on the starting structure. We need a methyl group here, right? So this is going to prefer to do things in a Markovnikov addition. Let's go ahead and put this down. So regional selectivity is present here, right? So hopefully you guys have looked it up. I'm going to write mark just out of convenience. So if we had to look at an alkene and we had to figure out which carbon is the mark or the Markovnikov carbon, which carbon would that be? This carbon with the methyl group or the carbon without the methyl? What will you tell me? The carbon with the methyl, right? Are you guys still with me in teams, or I'm just talking to myself? Hello, hello. Okay, maybe I'm not in team. Teams. All right, can you guys hear me in Microsoft Teams? Hello, hello.
Okay,
Okay, somebody says yes.
we can hear you.
Okay, I wasn't sure. All right, can you guys see the screen?
Yes.
Okay, good. So I'm going to do an addition of water here. All right. So technically, I should have an OH and an H added to the ring. All right. But in this case, there's a rearrangement. So what happens is that I go from something that's tertiary to something that's benzylic tertiary if I do a hydride shift. So my product is going to be this. Right? I'll put this in red. I'm trying to make this bold. All right, there's an H that's going to get added, and that original H gets added here. Right, I'm going to put that in gray. Okay, so that's the answer here. I'm actually going to deviate a little bit from the worksheet here because I want to cover all these three variations together. It should be hydroboration next. Okay, that's right. All right, what happens if I do this? All right, can anybody tell me what this reagent is going to do? All right, this is also hydration. Okay. However, this one occurs with no rearrangement, right? And the selectivity here is the same as the Markovnikov part here. All right, so again, we already established on the alkene that this carbon has had the arrow pointing to it is the more substituted carbon are the same as saying the Markovnikov carbon, right? So I need to form my product. And because I don't have a rearrangement for this case, there's going to be an OH added here. And my original H is going to be there. It's not letting me draw in my H. All right, and these two reagents do not have any control over the addition. All right, so that means that they will typically have racemic mixtures. So I'll write that note here shortly. All right, again, this H is not typically drawn. I'm just drawing it for teaching purposes. All right, so that means that there's no control. You get a racemic mixture, right? For this addition and for the addition on the bottom. Right? Again, there's no control again racemic mixtures. All right, let's take the same reagent again. All right, and this stuff is known, it has a more fancy name. This is an oxymercurization. It's the first step, and the second step is a deoxymercurization. All right, you don't have to be that technical with that. As long as you recognize that this is a hydration reaction that adds the OH to the more substituted carbon, you're going to do well. All right, let's take a look at this second or this third reaction here. What if I give you one that has this BH3 and hydroxide added? Right, I gave you guys the fact that this is a complex with THF. Right, and then step 2, there's going to be sodium hydroxide, hydroperoxide, and water. Okay, what is this doing? Did anybody figure this out? All right, did you guys try this? All right, this is also an hydration. This is why I wanted to cover this one right now. All right, this one has no rearrangements. And the regional selectivity is going to be anti. So what does that mean? I'm going to end up adding my OH, not to the substituted side, but which side?
The least substituted side.
That's right, the least substituted side. Right, so now I'm going to generate.
Dr. Cooper, Jalen needs to be let in.
All right, I just let some people in. All right, I just let her in. All right, I'm gonna have to just color all this to normal black. This is not working. Okay, and I'm gonna get this compound now where my OH is on the least substituted side. All right, there's something unique here that I'm trying to draw, and it might be better just to use a wedge instead of those lines here. All right, hydroboration does have control, and this is gonna be addition. Right, so that means the H and the OH that's added adds to the same side. So let's review our 3 ways of doing hydration. Let's see if I can get this to zoom in a little better. This might be the best I can do. All right, whatever I just have in plain acid, this could have been ACl, that could have been H2SO4, any acid here with water is going to do a hydration, all right? But it's going to be prone to rearrangements. All right, you guys want to recognize here that the carbon cation that forms here will be tertiary, but next door it will be tertiary. So this will rearrange itself to where the OH is added to this position, and the initial H will be added here. Okay. The second way of doing hydration is the oxymercurization, demercurization step. All right. So here, this is another way to do hydration, but this is not prone to rearrangement. So now my OH is added to the carbon that was most substituted originally, right? The second way of doing the hydration is the hydroboration step, right? Where I take borane and a little bit of hydroxide and hydrogen peroxide with water. This does a anti-Markovnikov addition to now my OH is added to the least substituted carbon, right? There's three ways of doing hydration. You want to know the advantages of doing each version of it, okay? Let's keep moving forward. Let's do document settings. Make this page a little bit longer. Yep, modified all those. Let's keep coming down. Okay, next on our list is HBr. What's going on here with HBr?
The hydrohalogenation.
Yeah, that's correct. This is a hydrohalogenation. All right, can you tell me something about its selectivity, region selectivity? Can you tell me where the groups typically go? Is this a Markovnikov or anti-Markovnikov? You guys remember?
So
All right, so this one, unfortunately, is prone to rearrangements. Put that here. And the regional selectivity for just plain old HBr is Markovnikov, right? So normally my Br, which is the largest atom, would be added to that carbon. But what's going to happen? Because of the rearrangement, right? A better carbon cation forms at the tertiary site. So my product here we'll put a Br here instead, right? And that initial H is put here. All right, again, you don't have to show the H. The H's are understood on carbons, but we're just drawing this in for teaching purposes, also to kind of mentally keep track of the mechanism. Right? Okay. But good, good. You guys got the class of the reaction, right? That's a start. All right, let's do this. I'm going to jump around a little bit, but I'm going to do HBr with ROOR, right? And ROOR, was anyone able to look this up? All right, that's a peroxide, okay? All right, and typically to run this, you would need some light here. I just need the V. All right, good. So what type of reaction is this? Can anyone tell me? This one is the same class. This is a hydrohalogenation. That means I'm adding an H in a halogen across the ring. All right, conveniently, this one is happening with no rearrangements. And this reaction is important to learn because the regional selectivity changes from Markovnikov with regular plain old HBr, but if I mix it with peroxides, this is going to be a anti-Markovnikov addition, right? So if I had to examine my product here, all right, now my Br goes to the least substituted carbon, all right, and up top, H from HBr added up top. So let's go ahead and do this. put this here. All right. So what's happening here? I'm gonna again take a look at that video to kind of understand this mechanism. But this gives you some insight into why peroxides, like hydrogen peroxides, are stored in dark bottles. Right. When hydrogen peroxide sees light, it's going to do a homolytic cleavage. All right. So this mechanism is a radical mechanism. You're going to form a radical. That radical is going to interact with HBr to form a Br radical. And that radical is going to bite into this double bond here, right? And at the end of the day, this is going to add a Br here because the radical that forms when you add Br here would be a tertiary radical, all right? And that radical is it's pretty stable. There's no hydride shift for radicals, so that means that you do not rearrange. So this radical is just more stable, and then eventually it's going to terminate with an H from HBr to generate the final product. All right. So again, take a look at that video to kind of get a feel for the mechanism. All right. But for right now, what you guys should know, all right, is that hydrohalogenation with peroxides is going to give a anti-Markovnikov product, right? And again, for this chapter, I want to make sure I say this. The mechanisms are not, we're not going to ask you the mechanisms for all of these compounds. You should know them. So I will present them to you, but you don't typically get exam questions where you need to know all the mechanisms, right? But knowing the mechanism is a big help. If you can't memorize what the reagent is doing, maybe you can picture the mechanism in your mind, okay? So that's good. Let's keep moving forward here. All right, again, I'm skipping around for teaching purposes, I think. If I kind of move in a certain order, I can make some points that I would like to make. So I'm going to skip to this hydrogen gas over, we're going to do palladium that's been treated, or carbon that's been treated with palladium. Can anyone tell me what this step is? Did anybody find this out?
Hydrogenation.
Yeah, that's right. Very, very good. This is known as a hydrogenation reaction. Right, what is hydrogenation doing? Can you guys tell me?
An addition of molecular hydrogen.
Yeah, definitely. Let's head on, right? Good. So that means I got to know where that adds to. And again, we know it's going to be a double bond, right? So the double bond here is going to be added. And typically we write SS if we're working with triple bonds, but SS is just saying that we're not going to leave any double bond behind, okay? So this reaction is going to add molecular hydrogen across the double bond. So that means I'm going to get a H here and an H there. All right. Now, typically, most people do not draw the H's in. All right. I'm drawing the H's just for illustrative purposes. So typically, you would see an alkene go down to an alkane. All right. That's the normal way of showing that. All right. But because I want to make sure that we talk about all the features here, the double bond is just adding two H's across it. All right. They're going to be adding in a syn addition. Right. Take a look at the video for the explanation there. But palladium is like a support. It's like a flat table, if you want to think about it. And all the hydrogens on that table are pointing up. All right. So that means that when palladium with the hydrogens attached to it reacts with a double bond, the two H's are on the table, so they add on the same side, right? Just like two plates when they come together, if there's something in between the two plates, they can only add from the same side that the plates are approaching, right? One H cannot come from the bottom and the other from the top. Instead, both H's come from the same palladium source, palladium table, right?
But
So
in an anti situation, it would be bottom and top.
yes,
Well,
exactly. If you could add two hydrogens anti, one would be wedged, the other one would be dashed. That's right. But with this catalyst, there's no way of doing that.
Okay.
Okay, good question. All right, I'm gonna go ahead and jump to the other version of.
Wait, what about the With the selectivity, the regional selectivity.
Oh, yeah, there's no regional selectivity. That's a good question because both atoms are getting the same thing.
Because what?
Both of the carbons in the double bond are getting H's. So if you get the same thing, I can't say it's Markovnikov or anti-Markovnikov because they're both are getting the same atom, right? And regional selectivity refers to the heavy atom, so the larger of the two. So if the bromine goes to the least substituted side, we say anti. If it goes to the more substituted side, we say Markovnikov.
Mhm.
In this case here, both carbons are getting the same atom. So I can't tell which one is more heavier, right? They're the same thing.
So,
So,
question.
yep, go ahead.
So the more substituted side would always be like towards the right of the
So in this case here, it's the one that has this methyl, right? So if you look at the two, this side has two carbons attached to the double bond up here, and this carbon only has one. Now it depends on the substrate. I just drew it this way for this example, but there could be one where I didn't have this methyl here and I had something else here. That you would say that this side is more substituted.
Oh, okay.
But I'll put this in here. No regional selectivity if that helps. Both atoms are the same that are added to the double bond, so we can't say what's going on there. Okay, good. Let's keep moving forward. All right. I want to do, and I should have did this earlier. I want to do this with this mixture here. I got this diiodomethane. I'm sorry, this is copper iodide. Get my letters right here. I got some zinc metal and I have copper 1 iodine. Can anyone tell me what this mixture is going to do? All right. This is why I felt like I should have did this earlier. This is another cyclo. That one more time?
Oh, I was going to say the cyclone.
Yep, that's right. Cyclopropionation. Very good. This is a cyclopropionation reaction. All right. So there's two flavors of doing cyclopropionation, which you guys learned the first example and this one, right? Why do we have two ways of doing the same chemistry? It comes down to what's on your substrate, really. So the first compound, let's scroll up here, that takes this azyl methane complex with light. If you have anything on your molecule that's sensitive to light, you can't use this method. Well, this is probably the cheapest way of making a cyclopropane ring. But just in case you have bromines or something else that could cleave off or could form radicals, this will be a little difficult to work with. So if your compound is light sensitive, you can't do this. Instead, you would use this version down here, all right, to do your cyclopropionation. Typically here, this works with all compounds. All right, this is pretty famous to make cyclopropane rings. The trick here is that this is a expensive, and if you are in the drug market, this would be a no-no because typically your compounds, your products will have trace amounts of metals, right? And those metals are an issue for drugs. You don't want to give someone a compound that has a little bit of zinc or a little bit of copper. Eventually, those people will get sick, right? So pharmaceutical companies would prefer to do the first one if they can because it's kind of all carbon-based. All right, so again, I'm just going to draw a 3-member ring attached to where the double bond was present, right? This reagent has its own name. It's called the Simmons-Smith reagent. Again, those technical details are not important. If you go to grad school, sure, they will hopefully like to hear that you know the name of the reagent, right? But if you're not heading that way, you A-okay. All right, there's no regional selectivity here, all right, and there's no rearrangements. All right, I'm hoping everyone is comfortable there. All right, let's keep moving forward. I'm going to take the same reagent Now I want to introduce it to OSO4. All right, this is known as osmium tetraoxide. All right, what is this going to do? Did anyone figure this out? Is that yes or no?
Epoxidation.
Die.
Okay, this one is, I hear somebody starting it, a dihydroxylation.
Mm.
Good, good. So that's the dihydroxylation reaction. Okay, so what does that mean? What's going to happen? All right, so my compound, my starting reagent, is going to be added to it two OHs now, right? Hydroxide OH. All right, so I'm going to get my wedges here. I'm going to have an OH here and another OH there. Right. Let's go ahead and color these red. Right.
It's in addition.
All right. So there's some features here that's unique to this. This compound does a syn addition. All right. So that means that both OHs add to the same side. All right. Is there any regional selectivity for this?
No.
That's right. How do you know there's no regional selectivity?
Because they're both on the more substituted side.
Yeah, there's two of the same atoms being added across the double bond, right? OH, OH. So if you said this is Makotnikov, how, right? Makotnikov or anti-Makotnikov is looking for the larger atom, right? Where did the larger atom go? To the more substituted side or to the least substituted side? Could you make that discussion here? You could not, right? Because here and also another OH there, right? So there's no discussion of regional selectivity here. And conveniently, this compound comes with, or this reaction reacts with no rearrangements. All right, I'm hoping that there's a burning question in your mind is why does this happen this way? Why does this ascend addition? Why is there no rearrangements? All right, all those questions are answered in the mechanism. All right, that's why we teach mechanisms in organic chemistry, because we can see the flow of electrons and we understand how the chemistry reacts. And that explains why I get a syn addition with no rearrangements, because the way this reagent reacts with double bonds. All right. So again, I'm going to ask you guys to take a look at that video to be able to make sense of the mechanism. But again, the mechanism is really for organic chemists. If you're going to go to grad school for organic chemistry, I will highly recommend to really spend some time looking at the mechanisms. But for students that are trying to get through sophomore organic chemistry, the goal is to learn the reactions, what they do, and how to predict the products. The mechanisms are secondary to that process. So what if I gave you this compound and I gave you something called RCOO, call it O3H, all right? And I'm pretty sure I gave you a more detailed compound. I did, okay? And I told you that there's an example of this compound, right? And I gave you the name of it as MCPBA. Let's make that italicized. Let's go ahead and draw that compound out. Let's talk about this. All right, MCPPA stands for metachloral. I'm trying to give myself some room here. Bring this down, sorry. Metachloral, peroxy, benzoic. So when you see this R, I didn't finish the structure. I'm so sorry. O H. Right. These compounds are known as peroxy acids, right? So peroxide typically has two oxygens bonded to each other. So if you guys look at here, there's two oxygen bonded to each other. And then they have this double bond O, and then the two oxygens bonded to each other with an H at the end. So that makes it like an acid, like a carboxyl acid. So these are known as peroxy acids. So whenever an alkene sees a peroxy acid, and most people uses this famous peroxy acid. So this is a real life example, right? Which is the metachloral peroxybenzoic acid, right? These compounds are going to do what type of chemistry? Are you guys able to look that up? Is that a yes or a no?
No.
Okay, let's talk about it. I wanted to just highlight each letter.
Oxid, something like that. Oh wait, epoxidation.
Yep, that's going to make an epoxide. Yeah. So MCPBA is a reagent, or any plain old peroxy acid is going to make an epoxide. All right, so the term here is an epoxidation. And you guys have probably heard of epoxy resins or epoxides, potentially in glues, right? So a lot of the glues, they use these type of reagents to glue things down, right? So next time you buy some glue, take a look at it. That's like the Gorilla Glue, hard type glue. You might see the word epoxy type of stuff, all right? So what's an epoxide? It's another three-member ring complex, but instead of having a carbon there, there's going to be an oxygen in the center. Right. I wanted to color that red, sorry. All right. So is there any regioselectivity for these type of chemistry? Can anyone tell me? No regioselectivity. And can you guys see why there's no regioselectivity here? Both atoms of the double bond are getting what atom? Oxygen, right? This carbon is bonded to oxygen, and that carbon is bonded to oxygen, right? So could you tell me which side is getting the larger atom? You could not, right? Both atoms are getting the same atom, right? So that means that regioselectivity is not applicable for this compound or for this reaction. All right, and conveniently, there's no rearrangements here, right? So we just draw a three-member ring where our two carbons of a double bond are located. Okay, good. All right, let's keep working on this. What if I gave you step one? I asked you to use a peroxy acid, and then step two, I asked you to stir in some water. What's going on here? Did anyone figure this out?
Hydration.
It's kind of in the hydration form. Does anyone has any other clues? All right. These two steps together are known as an dihydroxylation. I wanted to cover this because we just did the main version of it with the osmium tetraoxide. So whenever I make a peroxide first and then I react this epoxide with water, all right, you guys should recognize that these three rings are reactive, right? And they are reactive because of ring strain, all right? These compounds are looking to open. So if you just take this thing and stir it in water, water is going to open this up. And in doing so, Now I'm going to have a compound that has a OH on that carbon and an OH on the bottom carbon, right? What's unique about the relationship between these two things?
They're up and down.
Trans.
Are they trans each other? So that means that whenever I do a dihydroxylation from the epoxide and water, this does a anti
Anti-addition.
addition. That's right. So let's look back. Let me see if I can minimize this a little bit. Just kind of make a summary review. If I use plain osmium tetroxide, I get a syn addition product, right? I do dehydroxylation, that's syn, right? So that's synthetically useful if I want both OHs on the same side. This is I want them on the opposite side. Make the epoxide and open with water. Now I get an anti-addition. All right. And conveniently, because both carbons are still getting the same type of group OH, there's no regional selectivity to concern ourselves with, and there's no rearrangements to concern ourselves with. Okay. So hopefully we're getting okay with that. Okay. Let's see what happens when we do BR2. All right, what's happening here? Can anyone tell me what type of reaction is this?
Halogenation.
Okay, very, very good. This is known as, let's make some room here. This is a halogenation reaction. What does that mean, halogenation? Anyone help me out?
Addition of halogens.
Okay, good, good. So let's talk in detail about this. What would my product look like? I'm going to have an alkene now that I add what across this double bond?
The bromine.
Yeah. I'm going to have a bromine here, and I'm going to have a bromine there, right? So what's unique about how my groups are oriented here?
Trans
Yes.
again. Anti-addition.
That's right. There's some control on how these groups are added. They always have to add anti to one another. Every halogenation will be an anti-addition. Is there any regional selectivity or rearrangements to concern ourselves here with?
Mm,
There's none,
No.
right? How do I know there's no regional selectivity? Where did the heavy atom go? Well, I went to the carbon that had the methyl and to the carbon that had no methyl, right? So I can't say there's any regional selectivity. Both carbons are getting the same atom. Is there any rearrangements here? There's no rearrangements, all right? And hopefully this burning question is in your mind. Why does Br2 add anti to each other in an alkene, all right? And you want to think about the mechanism, right? So this is the mechanism that explains this. There's something unique happens with bromine. One bromine adds, so the pi bond is going to attack bromine. You're going to break the bond and give a Br minus. All right, so that means that when this pi bond is used to interact with bromine, there's going to be a carbon that has a plus. Now, carbon will be up here. Sorry, that's a more stable carbon. Bromine is going to form something called a bromonium ion. All right, that's going to be a 3-membered ring with a bromine. And the second bromine can attack. But because this is in a ring, the other bromine can only open it from the back end. So that means that these two groups are going to be anti because of the backside attack. So these are a trans addition to one another. And again, I will have a video explaining the details of the mechanisms, right? But again, if you're taking sophomore organic chemistry to move on into another career that's not going to be organic chemistry, those mechanisms will not be asked on those exams that you need. But you do need to know the chemistry. You need to know that Br2 or any halogen would add across double bonds in an anti-addition format. Okay, I'm checking my sheet here to see if there's anything else that I missed with alkenes. Okay, there are some more reactions I have to switch to a triple bond here shortly. Okay, let's do one more of these really quickly. There's another one that we need to cover. All right, what if I gave you a multi-step reaction? Where's my eraser? All right, that had bromine 1, and then step 2, there was water. Hey, hello, hello. Yeah, you guys can come in. I'm sorry. Oh, I do not. I do not. Hello. Yeah, I'm in class. It's all right. Miss Ely and some students with Miss Ely, they're in classroom with us today. But we're almost done. We're gonna wrap things up here shortly. Okay. So what if I gave you these two steps together? I gave you Br2 with water. What do you think is gonna happen here? Does anyone have a clue?
Would it still be considered a hydration?
Somewhat. Okay, that's partly correctly. Anybody else has a clue?
Hydrohalogenation.
Yeah, who said that? Hydrohalogenation.
Yeah.
Okay, yeah, that's exactly right. This is going to be a hydrohalogenation. Right. Typically, that functional group has a name. It's called a halohydrin. Okay, so I'm going to put it here. That's the name. So a lot of people call this just a formation of some type of halohydrin. So what happens in this chemistry is that I'm going to form the bromonium cation that typically is formed here. And again, you want to look at the video that explains the mechanism on that. But then water breaks it up. So I'm going to end up generating Br here and my new OH there. All right. So my OH is always going to go to the more substituted side. So this is still classified as a Markovnikov addition.
So is there no
Yep, no control. Yep, good question. And typically, because there's a carbon cation intermediate that forms here, you're going to lose control. There's no control of how things act anymore.
So normally when there's no control, there'll be no wedge or dash.
Yeah, you don't have to draw the wedge or dash. Yeah.
Okay.
Because really what you're saying when I say no control, they're going to be 50% of the wedge version. So you can think about it like this. This is going to be a complex mixture. They're going to be mixtures where these are syn, both wedges. They're going to be mixtures of these when they're trans each other, right? So it's going to be a completely random mixture of compounds. So typically we don't really draw in this stereochemistry, right? And this functional group is called a halohydrin. What's important, I want to make sure I put a note here because you guys want to keep this in mind, that the OH has to add to the more substituted side.
Okay.
And it does that because that carbon cation is the most stable carbon cation. So water is going to add to where the carbon cation forms. The carbon cation is not going to form here, instead it does there, and that's why you get the OH there. And this is why you lose control, because of that carbon cation that has to form in solution. Okay. Right. And again, when you attack a carbon cation, you can equally attack from the top and the bottom. All right, so hydrohalogenation is the technical term. All right, most people probably will refer to this as the formation of a halohydrin. All right, for the most part, go ahead. I'm so sorry.
The regioselectivity is marked.
Yes, just go ahead and put that down here. I'm sorry. Yeah, this is a Markovnikov selective reaction. And rearrangements here, you technically can have rearrangements, but I don't like to generate questions with rearrangements, so I would say possible.
Can you do me and go back up to the peroxide?
Yeah, sure.
Just real quick.
Yeah, no problem. Give me one sec. Let me bold and blue this. Let me bold and red that. All right, so possible rearrangements are possible, but this makes this question extremely beyond the level of this course when you do have to do rearrangements, right? So typically all we're going to be interested in is for you guys to recognize that there's an OH that's going to add to the more substituted side. You'll be fine there, all right? So you want me to go to the, which one, the dihydroxylation version or just the regular version?
Okay, never mind. The ROOH with the HBr.
Oh, okay. Right here.
Oh, ROOR.
Yep. Okay. Good.
Okay.
All right, good. Yep. Two new little things come up. Peroxides are now important. So you could have used hydrogen peroxide. When I use the word R here, that's just any substrate. That could have been an H or carbons. You're going to have dimethyl peroxide. But typically, most people do this with hydrogen peroxide. It's pretty cheap to get. Right? So whenever there's an OO bonded, there's a peroxide. Whenever I have a carbonyl, a carbon oxygen double bond with the OO, this is known as a peroxy acid now. Okay. Good. All right, let's finish up really quickly. Now, things change a little bit when I have a triple bond. All right. So on my triple bond reagents, they also react in this chemistry. All right. I need to figure out which side is more substituted. That's still an important question here, right? So the side that's more substituted here is this carbon there, right? Okay. So there's two classes of alkenes, I guess, in a sense. We'll go ahead and try to work with both cases. All right. I'm going to put an H on one version. I'll put an ME on the other version. When there's an H on the end, this is known as a terminal. High, right? Just like the terminal from an airport. That means that there's the double bond is at the end of the structure. There's an H here. That means there's no other carbons on the other side of the triple bond. However, whenever there's another carbon on the end, so now the double bond is not the last carbon. This will be the last carbon. All right, the double bond now is referred to, or I'm sorry, the triple bond is referred to as internal. This is an internal alkyne. Okay. It's important for us to recognize the names of these two types of alkynes. All right, so let's say that I take a terminal alkyne, and this is the reason why we want to make things different here because the chemistry will be a little different. And I take something that was on your sheet as H2 gas, palladium, BaSO4 salt with some type of base, and I indicated that it should be a nitrogen type of base with alcohol. This seems like a very complex mixture. All right, we're going to simplify this term here shortly. Was anyone able to figure out what this was referring to? Yes, no, no, yes. All right. This is known as Lindlar's
Oh.
catalyst. Lindlar's cat. All right. All right. That's the name most people refer these mixtures to. Can anyone tell me what this does?
As an alcohol? Mm-hmm.
Okay. No, it's not going to add alcohol. This is a partial hydrogenation reaction. We'll talk about the full hydrogenation reaction here shortly. All right, this is partial. All right. So when I do a partial hydrogenation reaction, I'm going to have a double bond. I'm going to have a actually, I should have did this to the terminal alkyne. I made a mistake here. I apologize. This does react, but it's hard to get the product to look the way you want. I wanted to do this. Okay. So disregard this. I'm not doing the reaction at a terminal alkyne. Instead, I'm doing it at an internal. And I'm going to get this compound out, right? I'm going to draw the H's in, but typically you don't have to draw the H's in for this molecule. What is unique about the orientation of this compound? Can anyone tell me? If I asked you something about this alkene, can you guys tell me if it's a cis or trans?
Cis.
Yeah, that's right. So whenever I take an internal alkyne and I do Lindlar's catalyst, which is a partial halogenation, I'm always going to generate the cis alkene. Important to know, all right? That was on you guys' sheet, all right? That this would make a cis alkene. What happens if I take the same internal alkene and I react it with, I think I gave you guys sodium, but it doesn't matter. You can take sodium or lithium. Any one of these metals will be fine. And I dissolve this in liquid ammonia. Is anyone able to figure out this reaction? That base is not needed for this. All right, and I put that 0 there to let you guys know that that's sodium in the 0 oxidation state. So that means it's not sodium plus 1, all right? Instead, that's sodium metal. Silver is very soft. Okay. Was anyone able to figure out this?
I don't know, but I know it's anti.
Yeah. Well, okay. I understand you're trying to say anti. You're saying you get a trans product. All right. This falls again in this partial hydrogenation reaction. All right. We'll talk about why is this partial here shortly. All right. All right. This has a more technical name. People call this a dissolving metal reduction. I actually seen one of these done before, and this is kind of scary, but it's pretty cool too. The reaction turns blue. It looks like a lightning bolt is in the solution. And the professor that was running the reaction was like, yeah, it's actually like a free electron floating in solution. So it's a blue color. So this reaction is you're gonna be dissolving this metal, and eventually sodium is gonna be giving away electrons, and that electron is gonna be in the liquid ammonium solution doing the chemistry. So my product from this, someone did give me a pretty helpful discussion here. It's gonna be, actually, let's just delete this right quickly. All right, now my alkene product is gonna look like it's wet. It's trans, right? So I get a trans alkene, all right? So it's very important for us to recognize the significance of these two synthetic procedures. Lindlar's catalyst will give us the cis alkene, all right? And the dissolving metal reduction will give us a trans alkene, all right? If I took this, and if I reacted it with hydrogen gas, SS, what would I get? Anyone know? All right, this will be known as the full hydrogenation. And all full hydrogenations will generate alkane. Right? Let's do this then. Grab this right quick. So instead of having a triple to double bond, I'll go triple bond all the way to a single bond. I go to an. But whenever I do a full hydrogenation, I will always generate an alkene. Anytime I do a partial, I will stop in between at a double bond. Okay, so for the most part, we covered all the reagents on, oh, we did not. I'm sorry, there's one last reagent. And that's why I had it up here. All right. If I have a terminal alkene and I react it with sodium amide, right? This compound is a base. And all that happens is that I'm going to remove an H, right? And I'm going to generate, you could write like this. I'm sorry, that's not right. There's a bond there. You want it, but you want to remember that this really looks like where there's a minus charge on the triple bond carbon. That carbon right there will have a minus charge. I'm going to give it 2 lone pairs as well, so you guys don't forget that that carbon is going to gain 2 lone pairs. All right, and that's why it's going to have this form of minus charge. And the sodium is just a cation, so it's going to carry a plus charge. Right? These are the same thing. All right. This is known as an acetylene. So terminal alkynes have an acidic H. I'm going to go ahead and put a note here. You guys can keep that in mind. All right. This H is acidic. We talked about that. You guys remember the pKa of this is about 25, right? So this base is strong enough to remove it. Somebody's trying to join the class. Right? So this base is going to react with this H. It's going to be removed to generate this complex here, where there's a lone pair on this carbon, and it's going to have an attraction to that sodium. This is known as an acetylide. All right, so we cover all the reagents on that sheet. All right, I'm going to post the answer key again to Canvas to where you have that sheet to kind of make sense of all the reagents and what type of chemistry it does, what type of regional selectivity is present, and then also if there's any control of the addition. All right. There's going to be a video where I cover all the reactions and I'll talk about mechanisms in detail. All right. But that video is just for your records. All right. Again, you don't necessarily need to know all the mechanisms, but if you want to look at that just to kind of get the full lecture for this chapter, you'll be fine. All right. The last assignment that you guys will have to do before your final exam is to do a open note, open book, open class book test on these reactions. All right. Typically, I gave you 2 practice exams to kind of have the flavor of questions I'd like to ask. You're going to have questions to where you will need to know what type of reaction the reagent is doing. I might have a schematic where I take an alkene or an alkyne and I generate multiple products, and I might ask you what reagent does that chemistry. All right, so you want to be able to recognize what reagents should be placed over a reaction arrow to give the product. All right, I'm also going to ask you questions where I give you the starting reactant and reagents, and I ask you to draw the product. All right, be prepared for that. I will not ask any mechanism questions on this test. All right, so all the questions will either be provide the reagent, know something about the class of reaction you're dealing with, and to be able to generate the product. All right. I wish you guys the best of luck. That exam will not be due until Monday, all right? Because I'm not going to be able to upload it into AFRA. We have an event on campus for the chemistry majors today. So once I get done with that event, I'll be able to sit in my office and post that. So I'm not too sure how long that's going to get through with all that today. So whenever it posts, I'm not going to force you guys to try to complete it by midnight. I don't think that's fair. But you will definitely need to complete it by Monday, okay? Now, the next thing with that exam, it will be timed, all right? But it will not, well, no. I take that back. I told you guys it's not going to be timed. All right, so it's not going to be timed. It's not going to be using a lockdown browser. I'm so sorry. I made the wrong mistake. So you have up until Monday to complete it. I think everyone should be okay with that. All right. So again, please take advantage of looking at the practice exam, looking at the lecture notes, looking at the video that's going to post, and also looking at anything online that helps you, right? Khan Academy, there's a lot of organic chemistry tutors. There's a lot of things now that's present that I probably don't even fully know about, that you might know about. Use every resource that you can to help yourself, all right? The only thing that I'm not asking for is an expert answer, right? I know there's like programs or services like Chegg that defeats the purpose of taking an open note test. So please, I would prefer for you to answer the questions, not for you to submit back to me experts questions or expert answers, all right? And if you have any additional questions and things like that, just shoot me an email. I'm gonna be unavailable for probably the next 4 hours, but after that, I'll be able to look at emails if anyone has a question or anything like that. Okay? I hope this helps, all right, when it comes to mastering the chemistry that you will need to learn for these last 2 chapters. All right. With that said, I'm gonna stop the recording. All right.